Here in section 7.2, we'll be looking at trigonometric integrals, which involves using some trig identities to help us manipulate integrals that involve trig functions. So we'll focus mostly on a couple of specific forms where we have powers of sine, cosine, secant, tangent, and some variations of those. Before we get into it, I want to just quickly remind ourselves of some important identities. So we have the what are called the Pythagorean identities. So these were the ones that say, for instance, sine squared plus cosine squared equals to 1. Right? So this is more or less a right triangle Pythagorean theorem kind of identity. Notice that it allows us to isolate sine squared in terms of cosine squared, or vice versa, we can isolate cosine squared in terms of sine squared. So this is going to be useful in those kind of cases. Another Pythagorean identity was the one that involves secant and tangent. I can kind of remember how to get that one if I go through and I divide each of these terms by cosine squared. I get sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. Similarly, I could divide each of these terms by sine squared and we would get the other one. So sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared. And then 1 over sine squared is cosecant squared. So those are the Pythagorean identities. We'll see those are useful, again, for instance, if I need to write tan squared in terms of secant squared or vice versa. What are called the half-angle identities, we'll focus on ones that will just be the half-angle identities in the case when we're dealing with sine squared or cosine squared. And the variation of these identities that we'll use looks a little bit more like a double angle formula, but here I'm calling it the half angle identity because it's really kind of coming from that half angle formula. And so the idea is that if I have sine squared of x, I can write that as 1 half times 1 minus cosine of 2x. And then cosine squared of x will be 1 half 1 plus cosine of 2x. Okay. Now, why are these going to be useful? Well, in this case, it allows us to remove a power, or remove a square from a trig function. So, for instance, if I want to remove a power of 2, using this identity allows me to rewrite it in terms of something that does not have a power, because cosine of 2x now is a double angle. But actually, I'm going to most likely refer to these as the power reducing identities. Because that kind of suggests more what they're useful for. The double angle identities are ones that will also be useful, like sine of 2x is equal to 2 sine x cosine x. This will be useful from time to time. And cosine of 2x, actually, we notice that these identities up here are really just a variation of cosine 2x. So, for instance, cosine 2x I can write as cosine squared minus sine squared. If I replace cosine squared with 1 minus sine squared, I get 1 minus 2 sine squared. Solving for sine squared in that equation gives me the first formula here. Or if I were to replace sine squared with 1 minus cosine squared, I get 2 cosine squared minus 1, which then if I solve for cosine squared in that equation, I get this equation here. So really, you notice that these half-angle formulas are really the double angle formulas for cosine. So now that we've kind of seen an overview of these, let's try and integrate something that involves the power of cosine, in this case cosine cubed. And we'll think about the strategy later on, but for now let's just see how we can go about manipulating this into a form where we can find its antiderivative. So for right now, it's not entirely obvious what its antiderivative is. So what I can do, though, is I can notice that if I were to split one of the factors of cosine, what remains is a cosine squared. And then this cosine squared, well, I had that Pythagorean identity that allows me to rewrite this in terms of sine squared. And then by substituting sine in the equation, I can take care of this cosine here that we've split off. So I'm going to kind of save this cosine here because I'm going to do a substitution with sine in the future. Okay? So there's kind of two parts to this strategy. One is to try and rewrite this part in terms of sine, and the other is to try and save this cosine here that I split off for a substitution later. Okay, so we know that cosine squared we can write as 1 minus sine squared. And then again, leaving this as cosine x. Now this will be helpful when I want to substitute sine. Okay, so you see here we used the Pythagorean identity, so I was able to write cosine squared as 1 minus sine squared. And then we're going to save this cosine x for a substitution later. And we see now we're ready to substitute because we got 1 minus sine squared. And then the cosine x dx out here will become my du when I substitute sine. So I'm going to let u equal to sine x. And then du is equal to cosine x. Right, so that takes care of the cosine x dx that we have saved out here. And so my integral transforms into just 1 minus u squared du. Okay, and we notice that because it's just the polynomial integral now, it's much easier to integrate than what we started with, so integral is very simple. So integral of 1 will be u minus integral of u squared, which will be 1/3 u cubed. Gives us the antiderivative of this polynomial. And then replacing the u, we get our final result. So we have sine x minus 1/3 sine cubed. So we notice that this strategy really would work in any situation where I have an odd power of cosine. Because, or even if I had an odd power of sine. Because if I break off one of the factors, then what remains is something that has an even power, and then I can use the Pythagorean identity to rewrite that even power in terms of the other trig function. In this case, I had an even power of cosine, so I was able to rewrite that in terms of sine. And then I can substitute the sine. Here's another example that could use the same strategy. We notice that the factor of sine to the 5th has an odd power. So what I'll do is the same exact thing. I'm going to split off one factor of sine, and what will remain will have an even power. So we'll write sine to the 4th times sine. Here I'm going to save the sine over here. Okay, and then bring down the cosine squared. So we notice that here the sine is going to be what we save for the substitution. But then the trick is to rewrite the remaining trig functions in terms of cosine. Because if I'm going to save this sine x for substitution, I want to make sure to rewrite everything else in terms of cosine. So I don't need to change this cosine squared, but I do need to change this sine to the 4th. So here my goal is then to rewrite this in terms of cosine. Okay, so how will we do that? Well, in this case, it's sine to the fourth, so I can think of that as sine squared squared. And then I can replace that with 1 minus cosine squared here. So we'll have 1 minus cosine squared squared, and then another cosine squared out here, and then the sine x that we're saving. So we see now all this stuff is written in terms of cosine. So now I'm ready to just replace cosine with the u, and then the sine x dx that we're saving out here becomes du. So now we're ready to let u equal to cosine. Du becomes negative sine. And now we have negative from that negative there, right? Negative du. So the sine x here, sine x dx here becomes negative du. So I'll just put the negative out front. Then we got 1 minus u squared, quantity squared, and then another u squared out here. So what remains here again is another polynomial. But before I can integrate, I'm going to do a little bit of foiling. So I'm going to FOIL out 1 minus u squared. So we get 1 minus 2u squared plus u to the fourth. And then after I do that, now I need to distribute u squared into the parentheses. So I'll have u squared minus 2u to the fourth plus u to the sixth. Now we're ready to integrate. So then integrating, we'll have negative u 1/3 u cubed. And then here we'll have 2u to the fifth over 5. And then here 1 over 7 u to the 7. Notice I also, while I was doing that step, I also distributed the minus sign. And then finally we can put the u equals to cosine x back in. So we got negative 1/3 cosine cubed plus 2 over 5 cosine to the fifth minus 1 over 7 cosine to the seventh. There we have it. So we see that the same strategy that we did in the previous example was essentially what we did here, right? Where we have an odd power of sine. So we split off one factor of sine to save for a substitution. And then the remaining part that had an even power, we rewrote in terms of cosine, so that all the factors besides that one that we're saving involve a cosine. And then we substitute cosine. And then once we did that, then we had a polynomial integral that we were able to integrate.